I want to show you how to use your solubility graph to answer some of the questions that are on your worksheet and that you could find on your test. So remember, a solubility curve, this is going to show you how much dissolves at a given temperature. Now again, this is the amount of grams in 100 grams of water. You have to specify how much water, because if you have more water, you can always dissolve more. You will notice that most substances can dissolve more as the temperature goes up. There are very few that dissolve less. Now, NH3 is a gas. All gases are less soluble with higher temperatures. That's why if you have a fish tank, you have to monitor the temperature, because the dissolved oxygen becomes less as the temperature increases. So you have to maintain a certain temperature in your fish tank. All right, so one of the things that I could ask you, we could do this one, like KClO3, potassium chlorate. How many grams can be dissolved in 100 grams of water at 30 degrees Celsius? So you'd go across, you'd find your 30 degrees, you'd go up, and then you'd go over, and it looks like just a little more than 10. So maybe 11 grams, maybe 10.5 grams, you would estimate. Now, we can apply this to a lot of different situations. Like you're supposed to know the difference between unsaturated, saturated, and supersaturated. Unsaturated is when you have dissolved less than the maximum amount for that temperature. So if we were at 30 degrees Celsius and you only had 5 grams of potassium chlorate dissolved in that 100 grams of water, that would be considered unsaturated. This point right here is saturated. That's the maximum amount that can be dissolved at that temperature. If for some reason you were able to dissolve 20 grams at this temperature, then you would have a supersaturated solution. Remember, supersaturated solutions they're kind of rare because they're very, very unstable. It's like if you were carrying a load of laundry and you instead of using the laundry basket to take it to the wash machine, you decide to just carry the whole pile. And you drop a sock. So you stop, you pick up a sock, and guess what happens? Typically another one falls. That's because you're holding the maximum amount. Now, if somebody were to suddenly stop you and pile a whole bunch on top, you would be supersaturated because you're holding more than you really can, and it's very unstable. So as you're walking to the laundry room, one little bump and the whole thing could fall. So that's the idea behind supersaturated. To make a supersaturated solution, if I wanted to make it for KClO3, and I had 100 grams, I'd have to heat this up higher than 30 to get that 20 grams to dissolve. And then, so according to this, if you want 20 grams to dissolve, you're going to have to heat it up to 50. And then you let it cool down to 30. You have to go back. Once you cool it down and that stays dissolved, it doesn't fall out and fall to the bottom of the container, then it will be supersaturated. In most cases, as it cools down, the extra will come out of solution and settle to the bottom. All right, so one of your worksheets, this one right here, it comes right after that, it says a solution that contains 70 grams of NaNO3 at 60 degrees. Is it saturated, unsaturated, or supersaturated? So you're going to find your 60 degrees Celsius. You're going to find NaNO3, which is up here. So 60 degrees Celsius, NaNO3. If you look, it looks like it can hold about 125 grams. So what does that mean? Well, I would say if you only have 70 and it can hold 125, then that means this is unsaturated. Okay. Then it says, if unsaturated, how much more can the solution dissolve? We'll take 125 and subtract 70, and that's how much more you can dissolve in that amount of water. Okay. You'll notice it says, if it's supersaturated, how much solute remains undissolved. So again, you would still subtract. You're just going to end up getting a negative number because, again, it's holding it, but it's not holding it because it's falling out as crystals. But same thing. You're just going to subtract. So that's how you would use a solubility chart. The other item that isn't really just straightforward, but it's not hard, is Henry's law. Henry's law, again, relates solubility to pressure. And this is for gases only. Pressure does not affect the solubility of solids or liquids in other liquids. Remember, just think of your pop. If you have a bottle of pop, you can't see the gas in there, but we all know there's gas in it. That's what makes it fizzy. It's under pressure. The pressure pushes the gas molecules really, really close together, which means that they can attract to the water molecules that are in there and to each other, and that's how it dissolves. You release that pressure by opening it up, and instantly those particles are freer to spread out, and we start seeing the bubbles. So as the pressure goes up, we can dissolve more gas. As it goes down, we dissolve less gas. Henry's law is just a way to figure out exactly how much you can dissolve, because remember, solubility is how much can dissolve, not how fast, but how much. So they'll give you a question where it says the solubility of a gas changes from 0.95 grams per liter to 0.72 grams per liter. If the initial pressure was 2.8, what's the final pressure? So remember, solubility does have these big units on it. So you had that solubility, and now you're at 0.72 grams per liter. You can even talk yourself through this. You should be able to say what is happening. So here the solubility was higher, here it's lower. We always know for gases that that means that your pressure should be lower than your initial pressure. Now it's telling us our initial pressure is 2.8 atmospheres. Okay, what is our final pressure? So again, this is just one where you're going to plug it in. 0.95, I'm going to leave the units off. 2.8 is equal to 0.72 over P2. So you're cross multiplying, so you're going to get 0.95. P2 is equal to 0.72 times by 2.8. Okay, so remember, we're just cross multiplying. Then you're going to divide by 0.95. Again, this is the long way. Some of you are really, really good at your math, and you can do it much more quickly than that. Plug it into your calculator, which is what I'm doing right now, and our new pressure is 2.122. We only need 2 significant digits, so I'm going to stop there. My pressure was in atmospheres, so this one will be in atmospheres, and you can see that the pressure did go down as predicted.